Roman concrete contains features that modern quality control would treat as defects: white lime clasts, uneven mixing, reactive volcanic aggregate distributed unevenly through the matrix. The material is heterogeneous in ways that would flag for rejection in a modern cement plant. In modern concrete, those characteristics are warning signs, indicators of incomplete hydration, inconsistent performance, reduced structural reliability under load. In Roman marine concrete, they appear to be part of the reason the material keeps repairing itself. The Pantheon's dome has remained structurally intact for approximately 1,900 years. Its span, 43.3 meters in diameter, still the largest unreinforced concrete dome in the world, has not required reconstruction. Roman harbour concrete at Caesarea Maritima and Pozzuoli has survived 2 millennia of seawater exposure. Core samples from some of those submerged structures, analysed by John Peter Olsen of the University of Victoria and colleagues, showed mineral growth and mechanical properties that had changed, in some cases improved, over time, which is the opposite of what Portland cement concrete does in the same conditions. The question was never whether Roman concrete was durable. The question was, what mechanism kept it durable for that long? Portland cement concrete, the material used in virtually all contemporary construction, fails in marine environments from the inside. Chloride ions from seawater penetrate the concrete, reach the steel reinforcement, and begin corrosion. The steel expands as it corrodes, at roughly 3 times the original volume. Concrete resists compression well, but not internal tension. Cracks open. Seawater penetrates faster. The failure accelerates. The service life of a modern reinforced concrete marine structure is typically estimated at 50 to 100 years before significant repair or replacement is required. That is a range, not a law, but it is the working assumption of the engineering community that designs and maintains port infrastructure today. For most of the 20th century, attempts to explain the durability of Roman marine concrete arrived at the same impasse. Laboratory analysis confirmed that the material had different chemical composition and different mechanical properties: higher resistance to fracture, better behavior under dynamic loading from wave action. The analyses confirmed it was different. They did not identify why different translated to durable across 2 millennia. The explanations offered, superior craftsmanship, careful material selection, the general excellence of Roman engineering, were accurate as descriptions of outcome, but empty as explanations of mechanism. Saying Roman concrete lasted because Romans were good at making concrete is not an answer. It is a restatement of the observation. A major part of the mechanism became clear between 2014 and 2017. It required X-ray diffraction analysis, electron microscopy, and the synthesis of findings from marine structures across the Mediterranean. What it revealed was not a lost technique or a secret ingredient, but a chemical process that the Romans stumbled into by using a locally available volcanic material, and that continues to work in their concrete today. If you want documentaries that follow the evidence wherever it leads, consider subscribing. It means a lot to us. Now let's get into it. Roman concrete is not the same material as modern Portland cement concrete. Modern concrete is made by mixing Portland cement, a calcium silicate compound produced by heating limestone and clay to approximately 1,450 degrees Celsius, with water, sand, and aggregate. The chemical reaction that sets it produces a rigid matrix that is strong in compression but brittle in tension and vulnerable to the chloride and sulfate attack described above. The failure mechanism is well understood. What was not understood until recently was why Roman marine concrete did not share it. The binding chemistry of Roman marine concrete operated on fundamentally different principles. The primary binding agent was not Portland cement, but a mixture of lime, calcium oxide, produced by burning limestone at much lower temperatures, and pozzolana, a volcanic ash found in large deposits throughout the region around the Bay of Naples, specifically in the area around the town of Pozzuoli, from which pozzolana takes its name. The pozzolana used in Roman marine structures came primarily from specific volcanic deposits, particularly the Campi Flegrei caldera region, that have a specific mineralogical composition including aluminosilicate glasses, philipsite, and other reactive minerals. When lime and pozzolana are mixed with seawater, as they would be in marine construction, the calcium hydroxide from the lime reacts with the aluminosilicate compounds in the pozzolana to form calcium aluminum silicate hydrate, or CaSH, a binding gel that is chemically distinct from the calcium silicate hydrate produced by Portland cement and significantly more stable in marine environments. The CaSH gel has a lower calcium to silicate ratio than Portland cement hydration products, a structural difference that makes it less soluble in the alkaline conditions of seawater and less susceptible to the sulfate attack that corrodes Portland cement. The gel also forms a denser, more tortuous pore network than Portland cement paste, which slows the rate at which chloride ions can penetrate to the interior of the structure. These properties were not designed in. They are a consequence of the specific mineralogy of Campi Flegrei pozzolana reacting with lime under ambient marine conditions. This reaction was known to Roman engineers empirically. Vitruvius described the use of pozzolana in marine construction in De Architectura, noting that it hardened underwater and resisted wave action. But the chemistry behind it was not understood. Vitruvius knew it worked. He did not know why. The aggregate in Roman marine concrete also differs from modern practice. Rather than using inert aggregate purely for volume, Roman builders incorporated chunks of volcanic rock, tuff, basalt, brick fragments that contributed additional reactive surfaces to the mix. Tuff, in particular, contains aluminosilicate compounds similar to those in pozzolana, which means the aggregate itself participates in the pozzolanic reaction rather than sitting passively in the matrix. The result was a heterogeneous material with multiple phases of chemical activity distributed through its volume. Not a uniform matrix, but a chemically active composite in which different components reacted at different rates. This heterogeneity, which might appear to be a limitation of ancient materials processing, turns out to be functionally significant for the long-term behavior of the material. The 2014 paper by Marie Jackson of UC Berkeley and colleagues, published in American Mineralogist, was the first to identify a specific mineral in Roman marine concrete that had not been anticipated by the existing model of pozzolanic chemistry. The analysis began with core samples drilled from Roman harbor structures at Caesarea Maritima, Pozzuoli, and Anzio, sites chosen because they represented different construction periods and different marine exposure conditions, allowing the team to distinguish properties common to Roman marine concrete, generally from properties specific to individual sites or construction techniques. The samples were analyzed using X-ray diffraction, which identifies crystalline phases by the pattern of angles at which X-rays scatter off a material's atomic lattice, and scanning electron microscopy, which produces high-resolution images of the material's microstructure at scales of individual mineral crystals. The combination of techniques allowed Jackson's team to identify not just what minerals were present in the concrete, but where they were located, whether in the original matrix or in secondary formations that had grown after the initial cure. The samples from different sites were not identical. The Caesarea material had been submerged in relatively warm, high salinity Mediterranean water for 2,000 years. The Anzio samples came from a site with different wave exposure and different depth. The Pozzuoli breakwaters had been subjected to localized volcanic heating from the still active Campi Flegrei caldera beneath them, a geological condition with no equivalent at the other sites. What the analysis found across all three, despite these differences, was the same unexpected mineral, tobermorite, a calcium silicate hydrate with a specific layered crystal structure that forms slowly at lower temperatures than the conditions under which it was previously thought to crystallize. The conventional understanding of tobermorite formation required elevated temperatures, hydrothermal conditions well above ambient, that would not be present in a marine concrete structure sitting in Mediterranean seawater. Finding tobermorite at all three sites under different exposure conditions implied that something in the material's chemistry was enabling its formation at ambient temperature over long time periods. That was not consistent with the known behavior of pure calcium silicate systems. Tobermorite had been identified in Roman concrete before Jackson's work, but its presence had been attributed to the initial curing process, a high-temperature event during the early setting of the concrete. Jackson's team found something different: tobermorite crystals growing inside microcracks in the concrete. Crystals whose orientation and morphology were inconsistent with formation during the original cure and consistent with slow nucleation in the presence of flowing seawater over centuries. The crystals were not relics of construction. They were new growth, still forming in 2,000-year-old concrete. The mechanism, confirmed by the 2017 follow-up study in American Mineralogist, works as follows. Seawater percolates through the microscopic pore structure of Roman marine concrete over time. When it reaches areas where the lime has not fully reacted with the pozzolana, areas that remain chemically reactive even after the initial set, the calcium in the seawater combines with the aluminosilicate glasses in the pozzolana to nucleate tobermorite crystals. These crystals grow slowly, over decades or centuries, filling the microcracks and pore spaces in the concrete. The material, rather than degrading as seawater penetrates it, incorporates the seawater's mineral content into its own structure and becomes denser and stronger in the precise locations where degradation was beginning. The process does not stop. It continues as long as seawater reaches unreacted lime. This is not a property that was designed in. The Romans did not know that their concrete would respond to seawater by growing crystals in its cracks. What they knew was that pozzolana mixed with lime produced a concrete that worked in marine environments. The mechanism that made it work was operating without their knowledge or intention, driven by the specific mineralogy of the volcanic ash they were using and the chemistry of Mediterranean seawater. Once the mechanism was identified, a second question became unavoidable. If this chemistry works and modern concrete doesn't, what would it take to use it again? The implications for modern materials science are direct and have been actively explored since the 2017 publication. Portland's cement production contributes approximately 8% of global carbon dioxide emissions annually, more than the entire aviation sector. It is also the second most consumed material on Earth after water. The Roman formula requires lower firing temperatures, approximately 900 degrees Celsius rather than 1,450, and uses volcanic ash rather than manufactured cement, which reduces both energy intensity and carbon footprint significantly. If the tobermorite forming chemistry can be reliably reproduced at scale, the engineering implications extend well beyond historical interest. The practical obstacle to direct replication is the availability of pozzolana with the specific mineralogical properties of the Campi Flegrei deposits. Volcanic ash of varying compositions is available globally. Indonesia, Iceland, the Western United States, and Japan all have accessible volcanic ash deposits. But not all volcanic ash has the same reactive properties as the specific Italian material that Roman engineers used. The aluminosilicate glass content, the proportion of reactive minerals like philipsite, and the particle size distribution all affect the pozzolanic reaction rate and the conditions under which tobermorite nucleation can occur. Campi Flegrei ash is unusually high in reactive aluminosilicate glass compared to most volcanic ash deposits, a function of the specific magma composition of that caldera system. Jackson's team and subsequent researchers have been working to identify which mineralogical properties are most critical and whether synthetic or alternative natural materials can replicate them. Progress has been made in characterizing the chemical requirements. A globally deployable substitute has not yet been demonstrated at construction scale. A 2023 study, published in Science Advances by a team that included Jackson and researchers from MIT and the University of Houston, demonstrated that a lime-classed concrete, incorporating chunks of quicklime rather than fully slaked lime, showed self-healing properties under laboratory conditions when deliberately fractured and exposed to water. The unreacted lime chunks provided reactive sites that nucleated mineral growth in fractures, directly mimicking the mechanism identified in Roman concrete. The study was a laboratory demonstration, not a field deployment, and the authors were explicit about the gap between laboratory results and practical construction application. The research direction is established. The practical implementation is not yet resolved at scale. This is the current state of the work, not a mystery, but an open engineering problem with a known target and active research. The written record never lost the formula. Vitruvius described pozzolana and its use in marine construction in the 1st century BCE. Pliny the Elder described volcanic materials and their properties in his Natural History in the 1st century CE. These texts survived the fall of the Western Empire, copied in monasteries, consulted by Renaissance scholars, available to any medieval or early modern builder who sought them out. The recipe survived. The specifications did not. What was not in the record was the operational knowledge required to apply that information effectively. Which specific deposits produced the most reactive material, the correct lime to pozzolana ratio for different exposure conditions, how long the mixture needed to cure before loading, how to place it underwater without the mix diluting before it had begun to set. These details were in the practice, not in the texts. Vitruvius could describe the ingredients. He could not transmit the judgment of a foreman who had placed marine concrete in 50 harbors. When the practice stopped, when the engineering organizations that built and maintained Roman marine infrastructure dissolved with the Western Empire, the operational knowledge dissolved with them. The archaeological record of medieval construction in volcanic regions of Italy shows what this gap produced in practice. Builders around Naples and Rome, where pozzolanic deposits were locally available, did use volcanic ash in lime mortars throughout the medieval period. The mortars they produced were more durable than those made without volcanic ash. None of them approached the performance of Roman marine concrete. The difference is in the specifics that Vitruvius did not record: the Campiflegre deposits that produced the most reactive pozzolana, the proportions that maximized the pozzolanic reaction, the curing conditions that allowed the CaSH gel to develop fully before wave loading. These are not details a text written to describe practice can fully capture. They are the kind of knowledge that lives in the judgment of experienced practitioners and dissolves when the practitioners stop working. The distinction between knowing that something works and knowing why it works is exactly the gap that the 2014 and 2017 studies closed. Once the mechanism was identified, the engineering community had a specific target: reproduce the conditions for tobermorite nucleation. The ancient engineers who laid the harbor at Caesarea did not know they were optimizing for tobermorite formation. They were following a practice that worked. The research that identified why it worked is what makes deliberate reproduction possible. The assumption in most popular accounts of Roman concrete is that it was superior because Roman engineers were more careful or more skilled. The research suggests something more specific and more counterintuitive. Roman marine concrete benefits from imperfection. The unreacted lime nodules that remain in the concrete after mixing, which would be considered a quality defect in modern concrete production, where thorough hydration of the cement is a quality criterion, are precisely the sites where tobermorite crystal growth nucleates when seawater penetrates the structure. A more thoroughly mixed, more uniformly hydrated Roman concrete would have fewer reactive sites and would be less capable of self-repair. The physical process at a lime-clast is specific. When seawater reaches an unreacted lime particle embedded in the set concrete matrix, the calcium hydroxide at the surface of the clast begins to dissolve into the water. The dissolved calcium combines with the aluminosilicate compounds from the surrounding pozzolana, compounds that remain reactive in the matrix long after the initial cure. The reaction nucleates tobermorite crystals at the interface between the limeclast and the surrounding material. Those crystals grow outward into any available space, pores, microcracks, the void left as the limeclast itself dissolves, filling and reinforcing the exact locations where structural weakness was developing. The defect becomes the repair site. The incompleteness of the original mix is the mechanism of the long-term durability. The durability of Roman marine concrete is partly a function of what was left undone in the mixing process. The material works not despite its imperfections, but partly because of them. The mechanism that produces tobermorite crystal growth requires the reactive lime to still be present as discrete particles in the set concrete, available to react with seawater decades or centuries after the initial cure. This is the kind of finding that materials science produces when it looks at ancient materials with modern analytical tools, not confirmation that ancient engineers were wiser, but identification of specific mechanisms that operated without the engineer's full understanding and that can now be deliberately engineered for. The Roman builders at Caesarea were not designing for 2,000-year service life. They were following a practice that worked. The mechanism that made it work was running in the background, in the pores and microcracks of the concrete, without anyone's knowledge or instruction. If this was useful, subscribe for a new video every week. And if something here contradicts what you've read elsewhere, that's worth looking into. The sources are in the description. The Romans did not design a self-healing material in the modern sense. They used a volcanic ash that made seawater part of the concrete's long-term chemistry. 2,000 years later, that reaction is still not finished.